as I was telling you, we wanted to get rid of this verification for every subset of the inequality constraints that appeared in this kind of condition. So we were able to do this, and the idea is to look at this cone. Okay, this is the polar of the linearized cone. It's written as this form. It's all the positive linear combinations of the gradients, and if you can look at this set in this way, it's subspace. It's typically generated by this linear combination. Okay, every possible unconstrained linear combination of these vectors, you get subspace. And here there's a conic part of this condition. Okay, you add only non-negative multiples of these gradients, so it generates something like this. And it turns out that whenever you have a cone like this, you can separate the subspace part of the cone. Okay, so we define this set J minus of X. It's the following. Maybe here there's one gradient of an inequality constraint. Maybe you should think that usually it lies outside the subspace part, but it can happen that this vector belongs to the hyperplane. Okay, so if it belongs to the hyperplane, minus its gradient should belong to the hyperplane also. So minus the gradient of an inequality constraint should not be inside this set, because you only multiply positive multiples here. But it can happen if it can be generated by, if you combine these things, maybe minus the gradient of an inequality constraint belong to this cone. Okay, so we separate these indexes. We look at the point X, and we build this set of indexes, J minus. It turns out that this is precisely the set of indexes that should remain with constant rank. So our condition we call constant rank of the subspace component. So this is the subspace component of this cone, and we ask that this subspace, this set of vectors that generate this subspace has constant rank in a neighborhood of the point. So the idea is that when we move this point X to some neighboring point Y, the subspace part does not change dimension. The subspace part only tilts a little bit, and the conic part moves accordingly. Okay, so this is a constraint qualification that we define, and it is in fact weaker than every other one that I presented. Okay, it's surprisingly enough, it's weaker than the relaxed CPLD, because we are talking about rank here and not positive linear dependency. But we can prove that it's weaker, and that's mainly because the sign of the multipliers are contemplated here when we look at this cone. So I should show you one example. So it's one variable, 3 constraints. These are the gradients at the point X equal to 0. If I looked at all the constraints are active, and so the polar of the linearized cone is all the positive combinations that I can get using these numbers. Okay, so this is 0 at their origin, so it does not give me anything new, but I can get the whole here real line, multiplying this by a positive number and this by a positive number. So the cone is the whole real line. So the set of indexes of inequality constraints such that minus the gradient belongs to the cone is everybody. Okay, every constraint minus the gradient belongs to the cone. So if I look at the rank of this single set of vectors, No, there are no equality constraints, so I look at every inequality constraint belonging to this set. This has full rank 1, for every x. Okay, in particular in the neighborhood of 0. So the constant rank, the subspace component hold, but the relaxed CPLD fails. For the relaxed PLD, I should look at every possible subset of these gradients, and if I take this single set alone, this is 0, it's positively linearly dependent, but it is linearly independent in a neighborhood. So it's strictly weaker than the relaxed CPLD. And in this paper, we were able to prove a lot of properties about this condition. So this is published in Siam Journal of Optimization, and in this paper we proved the following. This is the only thing I will tell you about second-order optimality conditions. So it turns out that the relaxed constant rank, you can use it to ensure strong second-order optimality condition. The strong is the one that I presented in the first lecture. Typically, when nonlinear programming books, when dealing with second-order optimality condition, they impose linearly independence. So you have only one Lagrange multiplier. So for this Lagrange multiplier, you have this second-order condition. Okay, so it's well known that for the Mangasanian-Fromovitz constraint qualification, you can't prove any second-order condition. And the difficulty here is that for the Mangasanian-Fromovitz condition, you have a bounded set of Lagrange multipliers. In fact, it's an equivalent way to define the Mangasanian-Fromovitz condition is by saying that the set of Lagrange multipliers associated to this point is a bounded set. So for the other conditions that are weaker than the Mangasanian-Fromovitz, we have an infinite set of Lagrange multipliers. So you may have unbounded Lagrange multipliers. So for our conditions, they are not second-order optimality conditions, but the relaxed constant rank is. So we can prove that for every possible Lagrange multipliers, the second-order condition holds. There are some other works that they use Mangasanian-Fromovitz and some additional condition, but they can prove only that there exists a Lagrange multiplier that second-order condition holds. So for this relaxed and constant rank, you can prove it for every Lagrange multiplier. Okay, so this is we have some recent works on second-order conditions, but I will not mention it here. Another important property, and this holds for all these conditions that I told you, they are stable in the sense that they are not sensible to perturbation in X. So if this condition holds in a point X, and you look in a neighborhood of this point X, the conditions still hold. So this is important. If you have errors in your measurements, you won't get much trouble because these are stable conditions. And one condition that is very interesting is this. If you assume the constant rank of the subspace condition, remember that these constraints in this set J minus, they are inequalities, right? They inequalities such that minus its gradients belongs to the linearized polar of the linearized cone. So in some sense, let me come back here. If you have minus the gradient of an inequality constraint belonging to this set, in fact, you could get any scalar multiple of this gradient. It belongs to this set also. So maybe you should think that this inequality constraint is in fact an equality constraint. Okay, because you are not constrained to generate positive scalars. Since minus the gradient belongs, all its multiples also belong to this set. So this inequality is acting more like an equality than an inequality. And at this example, look that all these constraints, what's the feasible set here? It's only the origin. Only x equals 0 is a feasible point. So all these inequality constraints that belongs to the set J minus, if I look in a neighborhood of the feasible set, they are in fact equalities. There are no strict inequality, there are no feasible point that satisfies this constraint strictly. Okay, so we can prove this in fact. The inequalities in this set J minus, under this condition, they are locally equalities. So at this point where the constant rank condition holds, I'm looking at every feasible point in a neighborhood of this point, and I can prove that there are no inactive constraints at this point. So this is very interesting, and we have not exploited this enough. So I think that this may have some important practical applications, because you have a way to model your problem, and you are adding some inequalities, but they are in fact equalities. So maybe this could be exploited in numerical algorithms. We don't know how to do this yet. And another important property that holds for every condition that I presented, it's the one called error-bound condition. So it says the following: I have a point x here, where this constant rank condition holds, and it says the following: if I take y in a sufficiently small neighborhood of x, I can measure this y. Maybe it's not feasible. Okay, x is feasible, but if I looked at a neighborhood, maybe it's not feasible. So, but I can measure the distance of y to the feasible set by this infeasibility measure. So I can use the functions h and g that define the constraint set. This is similar to the penalization function that we used before, and in fact this could be changed to this using the Euclidean norm, and you could have here an equivalent definition. So it's very interesting that you can measure the distance, the actual distance to the feasible set, by looking only at the gradients. You have at least an upper bound to this for some fixed constant alpha here. And this condition is very well known in nonlinear optimization. It's related to sensibility of problems, and it's also related to proving convergence. So if you are able to show that this infeasibility measure goes to 0, then you know that your point is going to a feasible point. Okay, so this is very important. And in particular, there are some works of Professor Andreas Fischer from Germany, and he devised some Newton methods imposing only this condition. Okay, so it's a very interesting condition, and all these conditions are what we call practical constraint qualifications, in the sense that we are able to prove convergence of two KKT points using this kind of condition. Okay, so this was done in this paper, in this Siam paper. We did this for all these four algorithms: Augmented Lagrangian, Inexact Restoration. These both methods I will comment tomorrow, and SQP and interior point methods. So under these very weak conditions, we were able to prove convergence to a KKT point. And the idea to do this is very simple. We simply have to prove that these algorithms generate approximate KKT sequence. That's what we do. And the way we build this condition is by proving that the approximate KKT optimality condition is stronger than this optimality condition given by this constraint qualification. So this immediately gives convergence to a KKT point under this weak condition. Okay, so the approximate KKT condition is a key. It's a key concept here in practical implementations. Okay, if you have an algorithm that generates this kind of point, then you can connect it nicely with constraint qualification using these ideas. Okay, so maybe I should tell you about some other constraint qualification that it's not based on our work. So as I told you before, you have here the Guinard constraint qualification. It's the weakest one. But if you ask for equality of the cones, you can call this Abadi CQ. So this is also a constraint qualification. If this holds, you have this. And in fact, all our constraint qualification, they are stronger than Abadi. Okay, you can prove that under our conditions, the Abadi CQ holds. The cones should be the same. Not only they are polar, the cones are the same, in fact. There is this idea of quasi-normality by Hastiness, and this appears also in the book of Bertsekas that I mentioned before. And in this book, he uses this condition to prove the KKT condition. So the idea here is that you may have positive linear dependent gradients. Okay, this colors mu is non-negative. So if this is linearly independent, okay, this holds. But if this is positive linearly dependent, then you must have this additional property. So you should be able to prove that there is no sequence yk converging to x such that the violation of the constraints has the same sign as the associate multipliers. Okay, so this happens also with inequality constraints. So that idea that we used to using the external penalty method, you have some formula for the lambda k. It depends on the function h, and you can prove that if this is the case, you are converging to a KKT point. And okay, so in this case, this condition holds because there is no infeasible point here. Okay, so minus x squared is always less than or equal to 0, no matter which x. So you won't be able to find a sequence fulfilling this condition. So in this case, this is a case where quasi-normality holds, but the rank is not the same. This is independent than our work. Okay, so this is not weaker nor stronger than our conditions. And okay, in this case, you can prove that it does not hold. There is a slightly modified version of quasi-normality. Instead of asking that independently each of these terms are positive, you ask that the sum of these terms is positive. So okay, it's a little bit different. But in the end, you can prove a diagram like this. Okay, LICQ is the strongest one, and then they divide here to MFCQ and constant rank. These are independent. If there is no, this diagram is a complete diagram. If there is not a line between joining two of these boxes, then it's because we have a counterexample. Okay, or you can deduce this implication using some other lines. For example, LICQ of course implies quasi-normality, but you can get this following this implication. So this is a full diagram, and Our condition here, it's the weakest one coming from this line. It's weaker than every other one of this. But it doesn't have any relation with pseudo-normality and quasi-normality. Okay, so it's a different line, and they both end in abadi. Okay, so the difference here is that for our conditions, we can in fact prove convergence of algorithms, and for these conditions, we don't know any algorithm that is associated to this. So it's as bad as Abadi or Guinard in this sense. Okay, so that's what I said before. So what we call a practical CQ is a CQ that guarantees that if your algorithm generates approximate KKT point, you are in fact getting a KKT point. And so this every other one is a practical CQ, but these other ones is not. And okay, so it turns out that in this condition, the constant rank condition, is not the weakest practical CQ. In this same paper on Siam, we defined an even weaker condition that it is still practical. But the difference now is that it's not so elegant theoretically. You don't have any of this property of stability. You don't have an error bound. You don't have anything. So what we have is that it's a practical condition. You can still prove convergence of approximate KKT algorithms.
So this definition of practical is really very linked to the notion of approximate KKT. Is there any other sense in which you can say that a constraint qualification is practical that is not related to approximate KKT? Yes.
In fact, this definition of practical CQ appears only in this slide. There is not a published definition. But you can define, for every other possible sequential optimality condition, you can say that the condition is practical with respect to those algorithms that generate this sequential optimality condition. Okay. And in fact, there is, I will show you here what we did in this paper, but there is an ongoing work by Alberto Ramos. He's a PhD student in my department, and he's studying practical CQs associated to every other sequential optimality condition, and he was able to find the weakest constraint qualification associated to every other possible sequential optimality condition. I will comment on this in the very end of this lecture. So to define this condition, what we call CPG, constraint qualification, constant positive generators, we have to define this idea of a basis for a cone. So I have here some vectors, V1 to Vk, and I have two subsets of indexes. Okay, so then I can form the space of positively generated vectors. So for the vectors in the first index set, I will use unrestricted multipliers, and for the vectors on the second set of indexes, I will use non-negative multipliers. So we can always find a basis for this cone. So the concept of basis of this cone is this. You can generate this cone, we call this positive span of this object. So a basis is a subset I prime and j prime of indexes, such that you generate the same cone using this other set of indexes. So you can always find this basis, and you call it a basis. Here it generates the cone, and in order to be a basis, it should be positively linearly independent. So we should be able to find a subset I prime and a subset j prime, such that if you take positive linearly combination with non-negative scalars associated to the second sum, you should only get the trivial solutions to this equation. Okay, so you can always find this. The trick here is that, look that this set J prime, okay, it's a subset of J, the set of vectors that we were considering with non-negative multipliers. But the ones that we are considering as with unrestricted multipliers, it's you can transform some of them that were in J to I. Okay, so you have to do something in the way that we did before to look at some inequality constraints and treat them as equalities. This is the key idea to define this basis concept. And in fact, this set I prime will always be a subset of J minus. The inequalities that you will add here to I prime will be only the ones that are in this set J minus that I defined before. Okay, so with this idea, we have a nice, well-established, well-defined concept of a basis for a cone generated in this way. And maybe I should give you an example. I have here a feasible set consisting of these two inequalities, simple inequalities, at the origin. So the set of vectors that I will look is both gradients. And the first index set, I will not put anyone there, and I will put in J both indexes. So the positive span of this set of indexes is in fact the cone, the polar of the linearized cone. So that's what we want to do. We consider here in this first set the set of equalities, and in this second set the index of active inequalities. So then when we generate this, we have the polar of the linearized cone. Okay, so in this case, this gradient is 1, and this gradient is -1. Okay, so this is the cone, but this does not form a basis, because it's positive linearly dependent. If you add 1 and -1, you get 0 with a positive scalar. So in order to get a base, here you have to do this. You have to move one of these inequality constraints to the inequality set here. So I will take one as the basis, as an equality, and I will remove the other one from J from J. So now, if I write here the positive span of this index set, it's an unrestricted multiple of 1. So I generate the whole line as I did before. So this is in fact a basis for this cone. And this is non-zero vector. It's positive linearly independent. So we define our constraint qualification by means of this idea. So I have here X a feasible point. Initially, I will be the whole set of equality constraints, and the indexes of equality constraints, and J will be the set of active inequality constraints. And my set V will be all the vectors, equalities and inequalities, and I will simply call them F. Okay, so Fi will be Hi if I is in this capital set, and Fj will be Gj for the other set. Okay, but they are all F now for me. So if I take the positive span of this set, using this original index set, I get, as I told you before, the polar of the linearized cone. So we say that this CPG holds, the constant positive generator CQ holds at this point X, if I'm able to find a basis, I prime G prime, of this set. Okay, you can always find one base, but you should be able to find one particular base with this property. If I look now in a neighborhood, okay, so in the point X, these sets are the same. Okay, you generate this set precisely with these other indexes of positive linearly independent vectors. But for the constraint qualification to hold, what you need, in fact, is that when you move to a neighborhood, you must be able to generate all the original cone moved to this point y. Okay, they should not be equal. They not be equal, but they must be. This must contain the correct cone. Okay, for all y in some neighborhood of x. So for this CPG condition, we lose every nice property, but it is still practical. So we proved convergence of this line of algorithms that generate approximate KKT points. Let me show you here the idea of the proof, which is very simple. In fact, remember what we did before? We had, yesterday, we had a local minimizer, and we proved that we are able to find sequences xk, lambda k, such that this condition goes to 0. Here J is the set of active constraints. Okay, this is what the approximate KKT condition says. Okay, so this is what I prove. I start with an approximate KKT point, is x. It has these sequences, xk, lambda k, mu k, with this nice property, and I will assume that CPG holds, and I will try to take the limit here. So, since CPG holds, this is a vector from the linearized cone. Okay, it's a positive combination of the gradients using sets I and J. So I'm able to find, I'm able to write this same vector using other scalars and other indexes. So these indexes is such that I prime J prime is a basis for the cone at the point X. So since CPG holds, this cone contains this one, so I can write this vector using this combination of vectors. It's other indexes and other scalars. And the important property here is that at the limit, you have a positive linearly independent vector. Okay, at x, this vector is positive linearly independent. So I simply repeat the proof that we did yesterday. So it's something like this. If this set of multipliers here, this new set of multipliers is bounded, okay, you simply take the limit. Xk goes to x. For some subsequence, this goes to some lambda star, this goes to x, and this goes like this. And so this is 0. You have KKT condition. Otherwise, if this is unbounded, you can divide by the norm here, take a subsequence, this will go to 0, this will go to some scalar lambda I, this will go to some scalar, some non-negative scalar mu j. This, if you look at this as a single vector, you are dividing the vector by the norm, so the continuity of the norm says that the limit is non-zero. So you get here a contradiction with the positive linearly independency of these vectors. Okay, you are dealing now with this sets in the base. So we discovered this kind of condition by looking at this proof, what we could do to this proof work with weaker conditions. And okay, this is the proof, and it's very simple. So let me show you an example where this condition holds. Okay, I have here 3 constraints, and this is the gradients, and the point is 0, 0. So initially I don't have equality constraints, and all the 3 inequalities are active. So at the origin, I have 0, -1, 0, 1, and 1, 0. So I can, since here minus this gradient belongs to this set. This is J minus, this vector belongs to J minus. So I can remove some of this. So I can, here I move this gradient, 1, to then treated it as an equality constraint. And I remove the other. So if I do this, I have a basis for this cone. Okay, so if we look here geometrically, you have 2 constraints here, and I have 1 additional constraint here, x1 less than or equal to 0. And these are the gradients. 1 point here, 1 point here, and 1 point here. 1, 2, and 3. So the cone generated by these 3 vectors is this half space here. Positive multiple of this, a positive multiple of this, and a positive multiple of this. We generate this half space. So at this point x, what we did was we removed this vector f2, and we treated this vector f1 as an equality. So I can generate the same thing treating this as an equality, and I generate the same cone. And this is now positive linearly independent. So I have a basis, and let's look at the neighborhood. What happens? In a neighborhood, the gradient of f3 is the same, and the gradient of f2 and f1, they do something like this. Okay, you simply add something to the x1 coordinate of this vector. So they move to this direction. The x2 coordinate remains the same, but the first coordinate improves, it increases. So it has this form. Okay, so let me look what happens to the basis. So the basis now is looking at f1 as an equality. So I generate this whole line now, and I remove f2. Okay, so well, if I remove f2, I don't lose anything. I can generate the same thing. So what I can generate in a neighborhood is this half space, and what I should be able to generate is this cone here. This is what I can generate if I use the original set. So in fact, the basis contains what I could generate. So this is CPG holds here. It's one thing. It's very interesting about this condition. Remember that if I didn't have this third condition, x1 less or equal to 0, I would still have the same feasible set. Okay, it's this thing here. So this is a redundant condition. And this is exactly the example that I showed you in the very beginning, where Grignard CQ does not hold. We computed the polars, we computed the tangent, and we show that they are not the same. So here we had an original definition of the condition, of the set, and it was horrible. Grignard CQ did not hold. If I tried to apply any algorithm to this, in fact, this minimizer would not satisfy a KKT condition. Okay, the Grignard CQ does not hold. If I have a function that I wanted to minimize and the solution was at this point, this would not be a KKT point. Okay, so it was a terrible situation. But what we showed here is that if I included this redundant constraint, then everything goes well. Okay, so I included one constraint, and now this point is a KKT point, and I can apply an algorithm and it will work. So this is an interesting property because any other constraint qualification that we had before, this CPLD, linear independence, no one had this property. I couldn't, if I have a problem that does not satisfy LICQ, it's not linearly independent, I can't add another constraint and LICQ will not hold. I can't do this. So if it holds for a bigger set of vectors, it should hold for a smaller set of vectors. Many other constraints were in this sense. But the CPG, no, it's not the case. You can add constraint, you can add a redundant constraint, and you can fix your model should work here. So the message here is that you should not be afraid of redundant constraint. Maybe it will help you, as it happens here in this example. So just to end this part, there is this work of Alberto Ramos. He's a PhD student, and his supervisor is Paulo Silva from Campinas, and he's a co-worker of mine, a collaborator in these papers. So what he was able to show was to find the weakest condition such that this implication holds. So CPG or any other one is one of them. So he defined it and proved that this is the weakest practical one in this sense. So for the approximate KKT optimality, sequential optimality condition, this is the condition. Okay, it's a very simple condition. Instead of asking about this basis of the cone, he simply asks for this point to set mapping to be continuous. Okay, so I look now at the polar of the linearized cone, and I look at this as a point to set mapping. For every y, instead of at the point x, I had here x, so I allow here this x to change to some y. This should remain fixed, and now I have a point to set mapping. Okay, for every y, I assign a set. So you simply ask for continuity of this map. So, and this is the weakest possible constraint qualification that is practical with respect to approximate KKT. And in this context, because this cone is generated by these gradients, and these gradients are continuous function, this is equivalent to asking that this point to set mapping is closed. Okay, this is a well-known concept in point to set mapping. Maybe I should write it down here. It says something like this. I have point to set mapping, y, associated to a subset f of y. So this is a subset of Rm, and this continuity, we say that this mapping is closed or upper semi-continuous, it's the same thing, if for every sequence yk, it's closed at x. For every sequence yk that converges to x, and for every convergent sequence wk convergent to w, such that wk belongs to f of yk. So I have a vector yk in Rn, it's converging to x. So for each yk, I can compute the set associated to this yk. So I have f of yk, and now I take a sequence of points inside the set. So in fact, I take a convergent sequence. So the upper semi-continuity or the closedness of this point to set mapping simply says that w belongs to f of y, the limit of yk. Okay, so this is upper semi-continuity or closedness of this map, and in this case, since these are continuous functions, you have in fact lower semi-continuity also, so it is what is usually called a continuous point to set mapping. So this is a very interesting result. It's still unpublished, but it should be published soon. And he also did that. He has a technique for any sequential optimality condition that you have here. he's able to define a weakest possible constraint qualification that guarantees KKT points. So his PhD is based on this kind of things. And we are now working on second order conditions. So if I want an approximate second order point, so we have defined these things, and I want to find the weakest constraint qualification that ensures second order condition. So we are able to define constraint qualifications in this sense. So this is the end of this part. I have here some reference. This is the two papers that I cited. The one, this is the constant rank of the subspace condition and the CPG. This is the relaxed CPLD, and you can find all important references in these two papers. And I want to mention here this recent book by Ernesto Virgin. He's the leader of the optimization group in my university, and Professor Martinez, he's the leader of the group in Campinas, where I did my PhD. And they are the experts on the software. So they define, so they own the rights for the Algorithmic software, and they wrote this book of practical augmented Lagrangian methods. And in this book, you can find many interesting things about constraint qualification and sequential optimality conditions, and many things that I mentioned in the first and second lecture, you can always also find in this book. And okay, so since we have some time, we have 30 minutes, I will go back and talk about the interior point methods, if that's okay with you, if you don't mind. So let me open here. Part 1. So we will, in next lecture, we will focus on algorithms. So maybe I should start mentioning the interior point method here. Okay, so all we did here was based on the external penalty method, but you can do things very similar with the interior point method. Okay, so the interior point method is based on this idea of, instead of penalizing a point that is infeasible, you penalize with respect to a point that wants to get out of the feasible region. So you have a smooth barrier function B. B of x is non-negative, and it goes to infinity if you are converging to the frontier of the set from inside. Okay, so for example, you can have this kind of condition. If g goes to 0, this goes to infinity. So when you minimize here this function, maybe you can think that there are no equality constraints here. Or the equality constraints are easy to be solved in each sub-problem. So you solve this, you get a point inside the feasible set, and you are not, this barrier does not let you go out the feasible set. But since the solution is probably on the frontier, this mu k should go to 0. So you can do something very similar to what we did, but the difficulty here is that if you want to apply internal penalty method, and maybe now I will talk if there are no equality constraints, you should walk through inside points. And we have seen that these conditions that we develop, they do not guarantee the existence of an internal point. Okay, if you have one equality and you want to model it with two inequalities, you lose this property. You don't have an interior point, so you can't apply this kind of method, and you can't define these constraint qualifications that we mentioned. So, but okay, if you have a problem that is sufficiently interior, and this is typically if you have a Mangasarian from of its constraint qualification, then you are safe. You can apply the internal penalty, interior point method, and you will get a well behavior, good behavior. So I will mention here the case of interior point method to linear programming. So you have to minimize C transpose X subject to A times X equal to B, and X greater or equal to 0. So this is a standard form linear programming. You can always write a linear programming problem in these terms. And okay, so, but in fact, you can deal with convex programming in the same way. It's precisely the same. If you don't want to think at convex problems, you can think that this matrix Q is 0, so you have a linear programming problem. But if you want to think as a quadratic problem, you can add here any positive semi-definite matrix Q. Okay, so it must be a convex function. So for this class of problems, you can build the barrier subproblems. It's something like this. Okay, you have the objective function, the constraints. Now these difficult constraints, we move it to this easy constraint, and this is you penalize only with respect to this inequality constraints. So it's remember it should be minus log of minus the constraint. So since this constraint is minus x less or equal to 0, so you get something like this. And okay, so if I want to solve this subproblem, I can write the KKT conditions for this problem. So this is the objective function. The gradient of the objective function is here, C. The other part is here, Q times X. This is the Lagrange multipliers associated to this equality constraint. So note here that each line of this matrix A gives you the gradient of one constraint. So if you want to add here a linear combination of the lines, you must write this in this form. It's A transpose lambda. And that's it. Here it's the derivative, the rest of the derivative of the objective function. Derivative of logs 1 over x, and we can write this in this form. This is a matrix, a diagonal matrix, where in the diagonal you have the inverse of the variables. Okay, and this vector E is the vector of ones. Okay, so what we do, we call this term S. Okay, so we can rewrite this in this form. Okay, A transpose plus S. Okay, everything is here, and this equality, if I call S, capital S, the matrix where the diagonal is the vector S, you can rewrite this as this. Okay, and X and S should be positive. This is what I get if I want to solve this this problem. And in fact, for a convex quadratic problem, the solutions of these equations, or equations and inequalities, is equivalent to the global solution of this problem. Okay, so this in fact characterizes the global solution. So this is the KKT condition. You can write the KKT condition of the original problem in this sense. Okay, this is the gradient of the functions, the gradient of the multipliers associated to the constraints. S is the multiplier associated to the inequality constraint, this one. Okay, so you can put this, and this is the complementarity. The multiplier S times the constraint, that is X, this should be 0. Xi times Si should be 0. It's the complementarity measure. X is the simple inequality constraint. And X should be feasible, primal feasible, and S is the Lagrangian associated to an inequality constraint should be non-negative. X should be non-negative also. So the difficulty here is that this complementarity constraint is hard to deal with. Okay, so the simplex method, or more generally, active set methods, what it does is the following. You start with a point that satisfies all the constraints. Okay, so and you have to have a concept of a basis here. So a basis, you only look at some of the x's are 0 or some of them are non-zero. So if you look at this, you may guess, oh, okay, I will choose some xi to be 0 or some other si to be non-zero. Okay, so you can guess here, you can try to find, looking at this constraint, by choosing which is 0, xi or si. And the simplex method does this in a clever way, such that you can always start with a feasible x. So x, you can do this in a way that x is non-negative and fulfills this condition, but s may be negative. So what the simplex method does, it changes this choice of subsets. So you solve this and you look, well, this s is not non-negative. So I change the basis. So there is a clever way to change which of this point is in the basis. So you do this in a way that s becomes greater or equal to 0. So this is the idea of active set methods. The interior point methods, this is precisely the previous conditions that we have concluded. This is the condition for the subproblem. It gives something like this. Okay, so what we are doing is solving the subproblem for some fixed mu, and we are making mu going to 0. So look at the optimality conditions of this problem is converging to the optimality conditions of the original problem. So this is one way to explain why the interior point methods is converging to a solution. So I think that this is repeated here. This is complementarity. Active set methods try to guess the optimal active subset and changing it at each iteration. And the interior point methods uses epsilon mathematics. This is a phrase from Professor Gonzio. And the idea is to replace this difficult constraint by this easy constraint, and you force convergence, letting mu go to 0. So, and now what we do, you solve this system of nonlinear equations. Okay, you have here a system of nonlinear equations. You can ignore for a moment this difficult constraint, and this is simply a system of nonlinear equation. It's nonlinear because the variables appears here as a product. The variables are x, s, and lambda. So it's non-negative only because of this term. This other part is non-linear only because of this term, and this part is linear.
Excuse me, why do you make the problem easier adding mu there?
¿Cómo?
Why do you make the constraint easier when you include explicitly mu?
That's a good question. Here there is something that is combinatorial. Okay, either of one should be 0. So this is you can guess that this would be difficult to solve. And here it's not the case. So you have each x and each s is positive. They are also, if you want mu, every xi si should be, the product should be mu. Okay, so you don't have this combinatorial property. Okay.
So it's like, in a sense, in one case the feasible set will be a discrete set, in the other one will be a continuous set.
Yeah, something like that. Okay, so we can solve this nonlinear system of equation, and where f is this mapping. So it's a mapping, x is in Rn, s is in Rn2, and m and lambda is in Rm. And it maps to this vector that is also in the same space. So you can apply the Newton method here. So if you remember the Newton method, in one variable, it would be something like this. I want to find the value where this function f of x is equal to 0. So the idea of the Newton method is to start at a point xk and look at its value here, f of xk. So it's difficult to follow this nonlinear curve here. So what you do, you follow a linear curve. So this is easy. You build here the tangent line, and instead of solving the difficult term f of x equal to 0, you solve the linearization. So this point here is your new iterate. So you repeat this. If I do this again, I will get closer to the solution. So you approximate f of x by this linear function. It's f of xk plus f prime x minus xk plus the error term. So if I want this to be 0, I will solve this. This is better. I will solve this equal to 0. Okay, so I get the usual formula: xk plus 1 is equal to xk minus the derivative of f at xk inverse times f of xk. Okay, this is the Newton method for one function. If you have many variables on many functions, the idea is the same. The difference here is that you have a vector equation, and this is the derivative of the function. It's the Jacobian matrix. Okay, so you get precisely what I wrote here. In each iteration, you have to find this vector. This is the derivative. You have to find its inverse times minus the function. Okay, so you have to solve this linear system to find this vector. Okay, then you add this to the previous iteration. And for the internal penalty method for this function, you can easily compute its derivatives. It's this matrix, and you can solve this equation, and this will give you 1 Newton iteration for a fixed mu. Okay, so if you want to solve this with the Newton method, you fix 1 mu, you perform a lot of iterations, a lot of Newton iterations, and you find the solution. Then you reduce mu and do everything again. Okay, so it's an infinite sequence of infinite sequences. So the idea of the interior point method is to perform only 1 Newton iteration. So you perform 1 Newton iteration, reduce mu. Perform another Newton iteration, reduce mu. This works fine. Okay, so you have to choose an initial approximation feasible to the initial approximation should be inside the feasible set, this constraint that should be positive. You have an initial penalty parameter, mu0. And you must have a parameter here saying how you should reduce mu. So mu k plus 1 is simple gamma times the mu k. And you should have a parameter epsilon that gives you how you should stop. Okay, so in one iteration you compute the Newton direction using that linear system at this point, okay, the approximation at the current iterate. And what you do instead of using the complete Newton direction, the Newton method would tell you to go to xk plus delta x. Okay, so, but if maybe the Newton direction is too large, okay, so you want to walk not the full Newton direction, but a fraction of the Newton direction, in such a way that you remain inside the feasible region. You don't want x and s to go outside the feasible region, and maybe the Newton method will tell you to go away, to leave the feasible region. So you prevent this by choosing this step size alpha small enough. Then you update your mu and repeat. Okay, if your stopping criteria is not satisfied, so here your stopping criteria may be only the complementarity. So if complementarity here, this should be xk transposed sk. If this is a fraction of the initial complementarity measure, and this is very close to 0, you should stop. Otherwise, you increase k and repeat. This is the interior point method. And there are many things that I could say about interior point methods. Well, maybe I couldn't because I don't know much, but there are a lot of things done for interior point methods. In particular, you can show that it's a polynomial algorithm. So there's this idea of considering a merit function. So in the step size, instead of asking this step size alpha to be simply to remain feasibility, you should ask to choose the step alpha that minimizes some function. So this is unidimensional minimization. Your variable is alpha, and you want to minimize this function phi in this form, and this function is something like this. And the idea of this function is that you can prove that it goes to minus infinity. Okay, and this implies that the complementarity holds. So if you use this kind of step size, you can prove that you actually get you improve this function at each iteration. So you sufficiently improve it at each iteration such that you are in fact going to minus infinity, and so the complementarity will hold in the limit. And if you take the parameter gamma in this way, this tells you how you should reduce mu. There is a theorem that says that you will reach your stopping criteria in this number of iterations. So if you want epsilon, if you want a very small tolerance for the complementarity, you must perform here a larger number of iterations. But the important thing it's something as square root of n log of n. So it's a polynomial number of iterations, and at each iteration you simply solve a linear system. So in fact there are other implementations of interior point methods where instead of log of n over epsilon you have log of 1 over epsilon. So the complexity is square root of n log of 1 over epsilon. So and this is the worst case scenario. In practice, an interior point method usually does not depend on the dimension. So you increase the dimension of the problem and you perform always the same number of iterations. The difficulty here is that when you increase the iteration, the dimension of the problem, sub-problems are harder to solve. You have to solve a linear system with more variables and more constraints. So, but typically, if your problem is large and you can perform one interior point iteration, okay, so maybe to solve the problem, you will need 10 iteration, and the number of iteration in practice does not grow exponentially. And okay, so this is just some remarks. but I think you already know about this, that there are no direct method to solve a nonlinear problem. You must use an iterative method. An iterative method will generate a sequence of points that converge or not to the solution. But what I haven't mentioned yet is that when you implement this iterative method in a computer, real analysis does not hold anymore. Real number mathematics does not hold. You replace it with floating point operations, which has some flaws. And this analogy is not perfect. The real sequences generated by the computer, maybe they are not the same as the theoretical sequence that our theory predicts. But so the theory does not refer to this real sequence. It refers to the theoretical sequence, of course. But the theory is necessary if you want to avoid performing an infinite number of experiments. Okay, so the useful theory should be able to predict the behavior of these many experiments. But you should have in mind that there are some practical phenomena that the theory is not able to predict. Okay, but the relevant theory is the one that contributes in explaining this practical phenomenon. Okay, that's it for today.
Okay, thank you very much. So we finish for today, and we continue tomorrow with algorithms. So that's it for today.